Hello and welcome. In this video, we're going to be going over the reading notes for AP Physics 2 Geometric Optics. Please remember to pause or rewind the video as necessary. Let's begin. Section 21.1, Light Sources, Light Propagation, and Shadows. Shine the laser directly upward toward the ceiling. What do you see or not see? Now spray the water over the laser through the beam. Now what do you see? Write your observations briefly. Well, you might remember in class I asked you to look at Observational Experiment 21.1, in which case a very similar situation was used where a laser beam was shown through chalk dust sprayed through the air. When the laser is pointed at the ceiling, only a red dot is visible. When water is sprayed over the laser is scattered so that you see a majority of the laser beam that is directed at the ceiling. Not only is it scattered, but it's scattered and reflected into your eye. Right? That's the only reason why we see anything in the first place, is because light gets reflected into our eye. So some of that laser is making its way to its to its destination, and some of that laser beam is being reflected through the scattered chalk dust, and some of that scattering light is being reflected back at us. Explain your observations in terms of the ray model of light. Well, since a laser beam is a monochromatic means one color, a laser beam would just be represented as one ray of light pointing in one particular direction, as opposed to rays from a light bulb, candle, or sun, which radiate in all directions, and when they approach in objects, they do so with parallel rays. A light bulb is an extended light source because various points on the bulb create rays. Does each point on the bulb create a single ray? If not, correct this statement. Each point on an extended light source, such as a bulb, emits light in many different directions. And this was Observational Experiment 21.2 that really helped to highlight the difference in the one-ray model versus the many-ray model. A ball is held halfway between a light bulb and a white surface. It is observed that there is a small round dark shadow, an umbra, on the white surface, and that is smaller than the ball. There is also a much larger round semi-shadow called a penumbra. Explain why this is in terms of your answer above about extended light sources. The umbra is created when rays from the bulb extend over the edge of the ball on the same side. The penumbra is created when rays from the edge of the bulb shine over the other side of the ball. And you can see that like this. Explain why light rays from the sun and other faraway objects are parallel to each other when they reach the observer. The sun is so far away from the Earth that only light from the sun reaches small regions on the Earth. And it's like the light inside of narrow cylinders that extend from the sun to the Earth and can therefore be visualized as a collection of parallel rays. That would be reason why when you walk down the street and you see your shadow is a very deep, dark umbra. There's no penumbra with your shadow. It is a dark shadow. And again, that has to do with the fact that you are so close to the surface in which you're emitting your shadow on, in which the shadow is cast upon, compared to the distance of the origin of the light being the sun. And since it's so far away, it's just simply going to come to the Earth in the form of parallel rays, because it's only hitting a very, where you are on the Earth is a very minute portion, a very small percentage, and therefore appears as though it's coming in parallel rays. Since the rays from the sun are parallel when they reach the earth, the length of a shadow cast by a building can be used to measure the height of the building. Explain how this is done. Okay, this is how we can take a look at this one. Let's say we have, we'll draw this down below. So say we have a building. Okay, and I'm going to call this HB for height of the building. And the sun is shining over the top of it like that, and it's casting a dark shadow that's this long. Okay, and I'm going to call that SB for shadow of the building. Okay, then what you can do is, using the exact same idea, you can take a stick, a meter stick, put it like this, and you can see that a meter stick cast vertical on the ground like this, perpendicular to the ground. The light would come in at the exact same angle that it would over the top of the building. And so if we talk about this being HS, or the height of the stick, and this being the length of the shadow, so this is the shadow of the stick, you can basically set up a proportion. And that is, the shadow of the stick is proportional to the height of the stick, and the shadow of the building would therefore be proportional to the height of the building. And then you could use that and solve that proportion for the height of the building. Just go ahead and cross multiply at that point.
Section 21.3, Refraction of Light. State Snell's law of refraction. Draw a diagram showing air and water to explain the symbols in your equation, what they represent. Okay, so Snell's law can be written as N1 times sine of theta 1 is equal to N2 times sine of theta 2. Okay, now if we draw a surface and a normal to that surface, okay, let's say this is N1 and this is N2. For instance, N1 could be air. This could be air, for instance. This could be water, for instance. And we're going to say that N2 is a greater index of refraction than N1. Then light is going to come in at an angle, some incident angle that we're going to call theta 1, and it's going to bend closer to the normal with a smaller theta 2. Okay, so theta 1 is your incident angle, or your angle of incidence. Theta 2 is your refracting angle, or your angle of refraction. Refracted ray examples. In each of the following situation, an incident ray is drawn, passing from medium 1 into medium 2. In some cases, the ray continues into medium 3. Use solid lines. Draw the ray as it refracts into successive mediums. Using dotted lines, show the reflections from each interface. Okay. Now what I'm going to do is I'm going to represent this the following way. I'm going to use red to show reflection, and I'll use blue to show refraction. We're going to keep it color-coded since the incident rays are all black. Okay, so remember, we're using dotted lines to show the reflection, but it'll be red. So for the first one, the incident ray is coming in. Here's your normal. The first thing you would do is you would draw your normal to the surface, just like this, all the way through. Well, your incident ray is going to go at the same angle your refracted ray is. In other words, I should expect the reflected ray, to be going off at that angle right there. Same thing with number 2. Not so true with number 3. Since N1 equals N2, the line is just going to pass right through unrefracted, just like that, in a straight line. Which means if it's passing through unrefracted, it's not going to reflect off the surface. Okay, the surface is now here. Here's the first normal to that part of the surface, and we would expect the reflected ray to go off at that angle right there. Same thing. We would expect the reflected ray to go off at that angle right there. And same thing with example number 6, we would expect that reflected ray to go off at that angle right there. In other words, I'm going to do this one example right here. Theta 1 equals theta r. Angle of incidence equals angle of reflection. And that is true in each case. Except for number 3, where it doesn't reflect at all. Here's theta 1. Here's theta r. Theta 1, theta r, theta 1, theta r. They're all the same. Okay, so those are the reflections. Okay, now let's focus on the refractions. Now, the general rule of thumb is the higher the n, the higher the index of refraction, the more light is going to bend towards the normal. So in the case of number 1, okay, I'm going to number these off in case you haven't figured out my numbering system. This is 1, 2, 3, 4, 5, 6. So in the case of number 1, you're going from N1 to N2, where N2 is a medium of higher optical density. So you would expect the line, the refracted ray, to bend closer to the normal, making theta 2 smaller than theta 1. Okay, now in the case of number 2, it's entering a medium of lower optical density. So you should expect it to be bending farther from the normal. In which case, here's theta 1, here's theta 2, and you can see theta 2 is much larger than theta 1. Again, example 3, there's no angle of refraction. The incident angle essentially equals the refracted angle, if you want to think of it that way. It continues through unrefracted. Theta 1 equals theta 2. They're exactly the same. Therefore, there's no bending of light. In example 4, now notice what's happening here. Okay, you're going to go from medium 1 to medium 2. Medium 2 is more optically dense than medium 1, so I should expect the line to bend closer to the normal. But now, notice again, we have a new surface, a second surface. And right here, I'm going to draw a second normal. Okay, this was the first normal. Here's the second normal. Okay, where this is now my new theta 1. Right, so I've got old theta 1, and I've got a new theta 1. Well, check this out. This is theta 2, my index of refraction, and theta 2 really becomes my new incident angle over here. So I'm going to keep calling it theta 2 since two parallel lines cut by a transversal alternate interior angles are congruent. They're the same angle. Well, I'm going to be bending into... Now, it says that N1 and N3 are the same optical density. So this could be an example where it's air, glass, air again. That could be the example. And so it's going to bend at the same optical density that you see this right here. So you can see how it's bending. You would expect this line here to be parallel to that line there, because this medium is the same as that medium. Okay, and you would basically expect this angle here, which I guess we can call theta 3. It's like a new refracting angle. That angle should be the exact same as theta 1 over here. Okay, now in the case of number 5, N1 is less than N2, but it's less than N3. So what we should expect is something like this. So it's going to bend closer to the normal. There's theta 2. Now when I make my new normal, and here's my second surface, go. My second surface, I would expect it to bend closer to the normal yet again, like this. I call that, I guess, theta 3. So my theta 2 over here also becomes my incident angle, refracting angle on this side. And I guess we can call that theta 3. And the last example, we have N1, okay, is going to N2, and N2 is lower optical density than N1. So we should expect the line to bend farther from the normal. So I'm going to bend it away like that. And theta 2 is much greater than theta 1. Okay, but that theta 2 is going to be the same as this theta 2 over here, the incident angle, and I would expect the line to bend closer to the normal on this side over here. In other words, I would expect theta 3, since N3 is the largest index of refraction, that I would expect medium 3 to be the highest optical density. So I would expect theta 3 to be the smallest angle closer to the normal, closer than theta 1 was to its normal. A laser beam creates the beam already drawn in the diagram. 3 spots appear on the ceiling at the locations indicated by the dots. If N1 is greater than N2 is, N1, is less than N3 is less than N2, draw the beam's reflection upward from each interface and the beam's refraction into the lower medium. Okay, so let's figure this out. First, I'm going to draw the 2 surfaces. Make sure we understand where this is going to be drawn from. So we got that. Then we got the second surface right here. So this is the biggest. So N2 is the biggest. Okay. Then N3 is going to be the next biggest, and then N1 is going to be the smallest. Okay. So here's what it's going to look like. We're going to keep going at that same angle until we reach that point right there. So let's go ahead and draw a normal right there where that meets there. But I'm only going to draw it to this point because it's going to refract in a different way. Okay, so here's my first point. I should expect reflected light to come off of that normal where theta 1 equals theta r. That accounts for the first dot. Okay, now what happens next? Well, this laser light is going to refract closer to the normal, like this, but it's going to reflect off of that boundary. So I'm going to draw a new normal for here. Okay, I would expect it to reflect upward like this. And then as soon as it reflects upward, notice I'll have a new normal at this position here. And since this is air, you would expect the way it reflected here to be the same as it's exiting here. So, let me see. Oops, I think I did it too far. Let me actually back that up, try it again. Yeah, I was too wide with that. Let's take it a little more narrower. So it would be a little more narrower like this. There we go, that's better. I noticed right away that my angle is not the same because the way this looks, you see my line that I drew here is 4 units up, 8 units over, right? So I'm kind of using that as a guide. So if I keep this going, what happens? Okay. Okay. Now I'll just keep the whole thing in red just to use the same color. It's fine. Okay, so that accounts for the second dot. And then finally, the last dot, right, is refracting into a medium that's lower optical density than this one here. So we would expect on that last one, here's the new normal that's created. Here's your new, that's theta 2, which means that's theta 2 also. And you would expect theta 3 in this next one to be larger from the normal. So in other words, wider away. Just like that. Okay, there's our theta 3. It's going to bounce off that bottom surface at that same angle. It's going to reach a boundary of higher optical density, which means it's going to refract closer to the normal, like this. And then finally, it's going to refract again farther from the normal, to meet that dot over there. Notice this line, and this line are all parallel with each other. Why? They're all in the same medium, meaning same optical density, therefore they should bend all the same. Explain what index of refraction is and give the basic equation for it. Well, index of refraction is a measure of the optical density of a transparent medium. The variable, that we use for the index of refraction is the letter n. Now, there are two main equations that we can reference at this point. N is equal to C over V would be 1, or N is equal to theta O over theta N. Lambda. Lambda O over lambda N. C is the speed of light in a vacuum. V is the speed of light in a medium. Lambda O is the wavelength of light in a vacuum. Lambda N is the wavelength of light in a medium. So if you notice, the ratio for the index of refraction is always vacuum to medium, vacuum to medium. What values must the index of refraction have? Well, 1, it will never be less than 1.0. You'll find out why in a minute. And it is unitless. Okay, what medium has the lowest index of refraction? Well, that'd be air. Here's why. So N is equal to C over V. Well, the speed of light in a vacuum is 3 times 10 to the 8 meters per second. Well, it turns out in clear air, speed of light is also 3 times 10 to the 8 meters per second, meaning it travels through air the same way it travels through the vacuum of outer space. The units cancel, leaving you with a value of 1.0. Four slabs of material are stacked so that the interfaces between the material are parallel. Find the index of refraction of each material, assuming the rays of light shown entering from air. So entering from air is the first medium right here. So N air is equal to 1. We'll start with that. Okay, that would make this, we'll call this theta air. Okay, and then I'm going to break this down. This would make this theta 1 to go with N1. Okay, now this angle here is going to be the same as this 30-degree angle here. So this is also theta 1. Okay, and it's going to refract into the next medium. That 37-degree angle is the same as that 37-degree angle. We're going to call that theta 2 to match that. So this is also theta 2, and it's going into a larger angle, which means a medium of lesser optical density. In fact, that same angle was what we started with. So chances are this is probably air again, perhaps, sandwiched in between those layers of whatever. Okay, that would make this a 53-degree angle. I would call this theta 3, and then finally, we're going to a 30-degree angle. That would also be a 30-degree angle. I'll call that theta 4 and theta 4, and then this would be, I guess, back to theta air again, because you're exiting the slabs of material. Okay? So now to work the problem out, let's go ahead and divide our space into sections like this. Okay, and we're going to be working with this basic equation called Snell's law. N1 times sine theta 1 equals N2 times sine theta 2. Now this is the generic equation where N1 and N2 are the first and second medium. Okay, now I'm going to be using different number scheme because I have N air, N1, N2, N3, N4. So I'm going to be using, the numbers that correspond to these. All right, so here's the first one. In the first one, we're going from air into N1. Okay, so using our equation, we're talking about this interface right here. It would be N air sine theta air equals N1 sine theta 1. Now you're solving the equation for N1, and you're going to do that by dividing both sides by sine theta 1. So you'd get N1 is equal to N air sine theta air over sine theta 1. Plugging in, we have 1 is N air times, now if we look back at the angles, sine of theta air is 53 degrees. So sine of 53 degrees, we're going to go sine of 53 over the sine of 30 degrees. Well, that's the same thing as 1 times 4/5. I'm going to use fractions because that's about 0.8, which is 4/5. And sine of 30 is about 1/2, 0.5. Okay, so that would be the same thing as 4/5 times 2 over 1, which is 8/5, which is 1.6. So N1, right, is 1.6. Let's go ahead and label that. Okay, now in the next one, we're going to be using that interface right there where we're going from N1 to N2, and you're going from 30 to 37 degrees. Okay, so we're going from N1 to N2. So this one's going to be N1 sine theta 1 equals N2 sine theta 2. Again, you're solving the equation for N2, so you'll divide by sine theta 2. N2 equals N1 sine theta 1 over sine of theta 2. Well, N1, if you remember, N1 was 1.6, so we're going to substitute that. 1.6 times the sine of, and we're going from 30 to 37. So sine of 30 degrees all over the sine of 37. Well, that's the same thing as 1.6 times sine of 30 is 1/2 over sine of 37 is 3/5. Okay, plug that in your calculator and you get about 1.33, about 1 1/3. That's pretty close to water, so I'm thinking N2 is most likely water. 1.6 corresponds to somewhere between glass or plastic. I'm thinking some sort of acrylic plastic possibly. Okay, so there's N2. Now we're going to go here, which is the boundary interface between medium 2 and medium 3. Okay, so we're going to go from N2 to N3. So the equation we're going to use now is N2 sine theta 2 equals N3 sine theta 3. And we're solving for N3. You see how repetitive this process is. Okay, solving for N3. It would be N2 sine theta 2 all over sine of theta 3. So I'm going to take my value for N2, which was 1.33, times the sine. Now you're going from 37 degrees to 53 degrees. So sine of 37 degrees over the sine of 53 degrees. Which would be 1.33 times 3/5 over 4/5, which those will cancel, and it ends up being 3/4 of 3/4 of 1.33, which is basically 1. And finally, we're going to go N3 to N4. So N3 sine theta 3 equals N4 sine theta 4. Okay, so N4 is going to be N3 sine theta 3 divided by sine of theta 4. So my value for N3 was 1 times the sine, and you're going here from 53 to 30 degrees. So sine of 53 degrees over the sine of 30 degrees, which would be 1 times 4/5 over 1/2. Which is again 4/5 times 2 over 1, which is again 8/5, which is again 1.6. So N4 is about 1.6, N3 is about 1.0. And you can tell, guys, based upon the angles of refraction. Look, the angle of refraction here is the same as the angle of refraction here. So that means the index of refraction here should be the same as that one here. This angle of refraction here, or rather that angle of incidence there, is the same as that angle of incidence there. They're parallel. Parallel rays, equivalent angles. which means that should be the same as that, which should be the same as that, which is exiting the slabs. Okay. Section 21.4, Total Internal Reflection. Pop quiz. A beam of light passes from water into air, as shown in the diagram. The index of refraction of water is 1.33. Now, according to this picture here, that would make this N1, 1.33, N2, 1.00. Because that would make this theta 1, and that would make this theta 2. They call it theta r, but I'm going to call it theta 2 for this purpose here. The table below shows 3 different angles the beam can have in water. For each angle in the water, find the corresponding refracting angle and fill in the corresponding blank. So we're going to call this part A, part B, and part C. So let's go ahead and do that like here. Okay, so for the first one, the equation we're using is N1 sine theta 1 equals N2 sine theta 2. Okay, now, in order to solve for theta 2, you have to solve for sine of theta 2 first, and then take the arc sine of both sides. Okay, so this would look like this. If I solve for sine of theta 2, I get the sine of theta 2 equals N1 sine theta 1 divided by N2. Now what I'm going to do is I'm going to plug into that, and I get N1 is 1.33 times the sine of 30 degrees is my first N1 over 1.0, which is my N2. Okay, so what I have now is sine of theta 2 equals, when I put that in my calculator, half of 1.33, which is 0.67. Now, at this point, what I'm going to do is I'm going to undo this sine equation. Now, the opposite of a sine equation is an arc sine function. So I'm going to take the arc sine of both sides, like that. Arc sine cancels with sine, leaving you with theta 2. So theta 2 is the arc sine of 0.67, which is about 41.8 degrees. Okay, now same thing. We're going to go N1 sine theta 1 equals N2 sine theta 2. Sine theta 2 is going to be N1 sine theta 1 divided by N2. So we're going to divide N2 both sides, basically. That's where we'll start. And when we plug into this, we're going to go sine of theta 2 is equal to N1 is now 45. So we're going to go, N1 is 1.33, but the sine times the sine of 45 divided by N2, which is 1.0. So sine of 45 is 0.707. 0.707 times 1.33 means the sine of theta 2 is equal to about 0.94. If we take the arc sine of both sides, we get theta 2 is approximately 70.1 degrees. It's getting wider than the normal. So as this angle gets wider like this, right here, this angle gets wider as well. That's what's happening. So 70.1 degrees. Now, when theta 1 is 60 degrees, so N1 sine theta 1 equals N2 sine theta 2. Divide both sides by N2, right? And we get sine theta 2 is equal to N1 sine theta 1 over N2. When we plug into that, sine of theta 2 is equal to 1.33 times the sine of 60 degrees over 1.0. Now, what we notice in this one is that when we put this into a calculator, the sine of 60 is about 0.866 times 1.33, we get the sine of theta 2 is equal to 1.15. That is not possible. That is not possible because the max value that the sine of any angle could have is 1 or negative 1. 1.15 is over that, meaning there is no refraction. You're not going to get an angle. You're going to get an error. If you try to take the arc sine of 1.15, you're going to get what's called a domain error. It's not actually a domain error, it's a range error. Well, technically it's a domain error with the arc sine function because the domain of the arc sine is the same as the range of the sine. Explain the phenomenon of total internal reflection. Total internal reflection occurs when light goes from a higher index of refraction to a lower index of refraction. If the incident angle is large enough, the refracting angle will be 90 degrees along the surface. Okay, here's what we mean. Take your Snell's law equation. N1 sine theta 1 equals N2 sine theta 2. Well, theta 2 is going to end up being 90 degrees, and the sine of 90 is 1. So you end up with N1 sine theta 1, where theta 1 now becomes theta c, the critical angle, equal to N2. And if you solve for theta c, you solve for the sine of theta c, it's the ratio of N2 to N1, where N1 has to be greater than N2. Has to. Otherwise, you run into a domain error. Okay, and what this would look like visually is you would have your surface, you would have your normal, you would have your largest possible angle. This is N1, this is N2. Think of it as like going from, water into air, as an example. That theta c that is going to the surface is going to be refracting along the surface here. That means theta 2, right, ends up being 90 degrees. That's how we end up with that. The critical angle is the largest incident angle, largest theta 1, that creates refraction of 90 degrees along the surface between two media. So find the critical angle for the air-water interface. Use the critical angle to explain why you couldn't do the pop quiz at the beginning of this section. So let's do this problem. So you got surface. Okay, we're going air, water. Here's theta 1, which is, by the way, the same thing as theta c, critical angle. And theta 2 is going to be 90 degrees along the surface. Okay, so the equation we have is N1 sine theta 1 equals N2 sine theta 2, where theta 2 is 90. We have N1 sine of theta c is equal to N2, because sine of 90 is equal to 1. Sine of theta c is equal to N2 over N1. Sine of theta c is equal to 1 over 1.33, which when you put that into a calculator is about 0.752. If you take the arc sine of both sides, the critical angle for the air-water interface is about 48.8 degrees. Now, that means that is the largest angle that you can have. Now we go back and we look at the previous example in the pop quiz. We had no refraction when you had an angle larger than 45 degrees. 60 is larger than 48.8 degrees. Therefore, we get no refraction. In fact, what happens is if it's too large, like this right here is too large, it's just going to be internal reflection along the surface, and there is no refraction. Total internal reflection is when you have refraction along the surface of the boundary, creating a 90-degree refracting angle. Example. As shown, a beam of red light is incident on a glass prism of theta 1. You can see that right here. With the normal. The glass has an index of refraction of 1.65 for red light. When theta 1 is 40 degrees, the beam on the other side of the prism, theta 4, is 84 degrees. All right. Let's see how this is. Let's see how this works. First, calculate the angle of refraction theta 2 on the left side of the prism. So, see theta 2 right there? We're going to find that. Here's theta 1. That is theta 2. That's what we're looking for. So let's do a Snell's law problem. We're simply going to go N1 sine of theta 1 equals N2 times sine of theta 2. Okay. Now to solve for theta 2, you have to solve for sine of theta 2. So the sine of theta 2 would be N1 sine theta 1 divided by N2. We got to divide both sides by the index of refraction. What I like to do is plug in for these numbers here. So theta 1 is 1.0. It's air times the sine of 40 degrees divided by N2, which I think was 1.65 in the glass prism. Well, this is the same thing as sine theta 2 equals, when you plug all that in your calculator, you get roughly, let's do this together. So we're going 1 times the sine of 40 1 times the sine of 40, and then divide that by 1.65. Yeah, so we get about 0.3896, something like that. When you take the arc sine of both sides, theta 2 is about 22.9 degrees. So I'm just going to round it up to the nearest angle, say 23 degrees. So there's our theta 2. Right there. So that angle right there is about a 23-degree angle. Okay. Now, let's do a little math here to figure out what's going on, because if you look at what's going on here, this plus this has to add up to 90 degrees. So if we go 90 from 90 minus 23, that makes this a 67-degree angle. Now 67 plus 60 plus this have to add up to 180. So 180 minus 60 minus 67 is 53 degrees, which means 53 plus theta 3, right, are complementary. So now if I go 90 minus 53, that makes theta 3 equal to 37 degrees. Okay, so I need that to be able to do the next part of the problem. Okay. Using the same prism, describe a change to the setup that would result in total internal reflection of the beam on the right side of the prism. Well, to make the beam that would result in total internal reflection, it means theta 4 would have to be 90 degrees. It would have to be refracting along the surface like this for a full 90-degree angle. Okay, and that means that theta 3 would now become your critical angle. So theta 3 becomes theta c, and theta 4 would have to equal 90 degrees. Okay, so that's what's going on there. Okay, so we're going to go n of the glass, sine theta of the glass equals n4 sine theta 4. So if we solve for that incident angle right there, sine of theta 3, so that would be, I guess, theta 3, which is the same thing as theta c, right? If we solve for theta c, sine of theta c would be equal to n of the glass. Excuse me, no, not n of the glass. It would be, because this would equal 1, because 90, theta 4 becomes 90 degrees, sine of 90 is 1, and so it's n4 over n of the glass. There we go. So sine of theta c would be 1, because you're going into air again, divided by 1.65. And then you got to take the arc sine of that. So theta c, the critical angle, 1 divided by 1.65 is about 0.606. Take the arc sine of that, and we're looking at about roughly 37.3 degrees. That has to be the incident angle. Now, if you look, the angle is already 37 degrees. So you see you have to increase it just a little bit more in order for that to happen. Okay, so we're going to work the problem backwards, okay, because remember it says using the setup, describe a change to the setup that would result in this. So in order to make this angle be greater, this angle here has to be lower, okay, which means this angle is going to have to be lower as well. So let's figure that out. Now, 37.2 degrees, if we actually go through and do the math everywhere, okay, if this becomes 37.3 degrees, then this is not 53 degrees anymore. 90 minus 37.3 is now 52.7. And if I go 180 minus 52.7 minus the 60-degree angle at the top, we don't get a 67-degree angle, we get 67.3 degrees, which means this angle here, right, would be 90 minus that, or 22.7 degrees. So doing all that, if theta c, the critical angle, is 37.3, this makes theta 2 approximately 22.7 degrees, a little less than 23 degrees. Okay, now using Snell's law, we go backwards. N1 sine theta 1 equals N2 sine theta 2, and we solve for theta 1 this time to see what that incident angle should be. So sine of theta 1 is equal to N2 sine of theta 2 over N1. So sine of theta 1 would be N2, which is 1.65, times the sine of 22.7 degrees over 1. If you put that in your calculator and take the arc sine of that, we get theta 1 is approximately 39.5 degrees. So what we need to do in order to achieve total internal reflection along the surface here, this angle needs to be a little greater, which means theta 2 needs to be a little smaller, which means theta 1 needs to enter at an angle that is slightly, not much, but slightly closer to the normal by about a half a degree. That would change this from 84 to 90 degrees. Example. An oil film rests on a thick slab of glass with an index of refraction of 1.4, as shown in the figure below. A light ray is incident on the film at the angle shown. On the figure, sketch the path of the refracted ray that passes through the film and the glass slab and exits into air. Clearly show any bending of the ray at each interface. You are not expected to calculate the size of any angles. What we're basically going to do is we're going to use these numbers here as indicators of how much the light should bend. Remember, the higher the n, the more light bends closer to the normal. The lower the n, the more light bends far from the normal. Okay, and we're going to use that. Here we go. My first one is going to go from 1 to 1.7, so it's really going to bend close to that normal, just like that. Now, at that boundary, I'm going to create a new normal. New normal right here. Okay. And then at that point there, I'm going from 1.7 to 1.4, which is a lower index of refraction. So I'm going to be bending a little farther from the normal. Now, notice this angle here is going to be greater than that angle there, but less than that angle there. Okay, so we have a wide angle, but not quite as wide as that. And then finally, I'm going to create a new normal here. And this exiting angle should be exactly the same as this parallel angle here. Just like that. Example. Monochromatic light. Again, anytime you see monochromatic light, it's referring to a laser. In other words, it's a light of one frequency, of one color. Okay. Monochromatic light is incident on a glass sheet as shown in the figure below. At an angle of incidence of 60 degrees in the figure, sketch the path of light takes first time it strikes the two parallel surfaces. Calculate and label the size of each angle in degrees on the figure, including the angle of incidence, angle of reflection, and refraction at each of the two parallel surfaces. So we're going from 1 index of refraction of air from 1 to 1.5 in glass. Okay, so here we go. The first one is theta 1, which I'm going to call theta A for theta air. Okay, and it's going to bend closer to the normal, just like that. There's my theta glass. Okay, now my reflecting angle, theta R, should be the same. If this is 60 degrees, this is 60 degrees. Right, that's law of reflection. Reflecting angles equal incident angles. Okay, but we're going to calculate using a Snell's law equation what theta glass should be. Okay, and we're going to go N1 sine theta 1 equals N2 sine of theta 2. Okay, we're looking for sine of theta 2. So you have to divide by N2, so it's N1 sine theta 1 over N2, which would be 1.0 times the sine of 60 degrees over 1.50. So sine of 60 divided by 1.5 is about 0.577. Take the arc sine of that. Theta 2 is approximately 35.3 degrees. So theta glass is approximately 35.3 degrees. Okay, Now, it's going to bounce off that surface right here, right there, okay? And it's going to refract at the exact same angle it came into the air glass interface. So this is the same angle right here, which means this theta 3 is going to be the same 60-degree angle that you had to start with right here. The only last thing remaining would be my reflecting angle coming up like this, where theta r is also 35.3 degrees. Example. The table below shows the index of refraction for glass for red light and for blue light. The center of the diagram shows a beam of white light incident on an interface between the vacuum and glass. In the center of the diagrams, the glass forms a triangle. In the right diagram, the vacuum is in the shape of the triangle and it is surrounded by glass. Draw the path that draw and label the paths that the red and blue components of white light take in both cases. So you'll notice that in red light has a lower index of refraction in glass than blue light does. What does that mean? Blue light will bend more in glass than red light will. Okay. And then consequently, blue light will bend farther from the normal when it exits glass back into a vacuum or air. Okay, so what we're going to do is you have white light coming in, just like this. It's going to go straight through unrefracted because there's the angle, it's coming at the normal, so the angle of incidence would be 0, right? So it's going to just keep going through unrefracted. Now, at this point right here is where you have the exiting rays of light. Okay, that's where it's going to come from. Now, if this is a 90-degree angle, that makes this 60. That makes this 30 degrees also. Okay. Now, what's going to happen is, if I were to just kind of keep going with a dashed line right here, this is going to be 30 degrees, the same as this angle right here. What this tells you is that the red light is going to bend at a certain angle, a certain theta 2, but the blue angle is going to bend more. The blue light is going to bend more because it has a higher index of refraction. So theta 2 for blue light is going to be larger. Okay, so I'm going to call this, this is the blue. Okay, this is the red. Okay, and theta 1, as you can see, theta 1 is going to be 30 degrees in both cases. All right, so here's how we're going to break this down. Let's break this down. I'm going to split this in two. Okay, we've got the red and you've got the blue. Let's quantify this and see. So in both cases, we have sine theta 1, n1 sine theta 1 equals n2 sine theta 2. You're solving for theta 2. So sine theta 2 is equal to n1 sine theta 1 over n2, which means sine of theta 2 is equal to n1. Now, this is going to be n1. The vacuum is going to be n2 because we're talking about the exiting interface right here. So n1 is actually going to be the glass. Now, if we're doing red light, that would be 1.5 sine of 30 over 1.0. Put that in our calculator. 1.5 sine of 30 is 0.75 divided by 1 is 0.75. So the sine of theta 2 is equal to 0.75. And if we take the arc sine of 0.75, we get roughly that theta 2 is about 48.6 degrees, roughly. Now, the blue one's going to be very similar. We're going sine theta 2 is equal to n1 sine theta 1 over n2. So this time we're going to go 1.6 is n1. So 1.6 times the sine of 30 over 1. And 1.6 sine of 30 is 0.8. So the sine of theta 2 is equal to 0.8, which means theta 2 is approximately equal to about 53.1 degrees. So you can see that blue light is just going to bend more when it exits the glass than red light will. Now, if we look at the opposite side of things, again, we're going from glass into a vacuum-shaped triangle. It will continue straight unrefracted. Then it gets to this side over here, which if I continue this, what's going to happen is I still have a 30-degree theta 1. Okay, and this time I'm going from N1 to N2, where N2 is higher optical density. So I would expect the both to bend closer to the normal. So if this is 30 degrees, that's 30 degrees, I would expect them to bend closer to this normal here. Which one's going to bend closer to the normal? The one with the higher index of refraction. So I would expect blue to bend closer to the normal like this. Then I would expect red to bend a little farther from that normal. Okay, so in other words, blue is going to have a smaller theta 2 than red will. Let's quantify this. So we're going to go sine of theta 2 is equal to n1 sine theta 1 over n2. So sine of theta 2 is going to be n1. Now, again, n1 is what for red is 1.5. So we're going to go 1.5 sine of 30. No, I'm sorry, not 1.5. We're going from 1 to 1.5. N2 is going to be glass. So I'm sorry, I have this backwards. This is going to be 1 times sine of 30 divided by 1.5. There we go. So the sine of theta 2, so sine of 30 divided by 1.5 is approximately 0.33. Take the arc sine of that. Theta 2 is approximately 19.5 degrees. You can see it's a much smaller angle now. Okay, and finally the blue. We've got sine of theta 2 equals n1 sine theta 1 over n2. So sine of theta 2 is going to be equal to 1 times the sine of 30. This time it's for blue light, it's divided by 1.6. So sine of 30 divided by 1.6 is about 0.3125. Take the arc sine of that, and we're looking at about 18.2 degrees. So you can see blue is going to bend a little closer to the normal, meaning it's going to have a smaller angle of refraction. Section 22.1, plane mirrors. Well, a plane represents a flat surface, so we're talking about a flat mirror. Explain what a virtual image is. A virtual image is an image that appears behind or inside the mirror. Draw a line, a straight line is the mirror. So the straight line you see right here is the side view of a mirror. And you can see a candle is placed in front of the mirror. Draw what the image would look like on the other side of the mirror. Draw 4 rays that emerge from the candle and reflect off of the mirror. So we're going to use take our first crack at drawing what is called a ray diagram. Now, please remember, anytime, this is our general rule of thumb, any reflected ray, write this down, any reflected ray will always have a virtual, a virtual extension in the mirror. Now, what I call this virtual extension in the mirror, I just call it a back ray. So you'll hear me say the phrase back ray all the time. Every time you draw a reflected ray, we need to have a back ray, okay? And angle of reflection equals angle of incidence. So we're going to take a look at all of that and put that all together to find out where the image of this candle would be formed, okay? So we're going to use the multiple ray model, which means we're going to pick, I'm going to pick 2 different points, okay? I'm going to pick the top of the candle right here and the bottom of the box right here, okay? And what I'm going to do is I'm going to pick multiple rays that are sent out from both of those points and how those rays reflect off of the mirror. So let's try this. So I'm going to start, let's start at the candle top, okay? And I'm going to pick, a couple different ones that go. So I'm going to go, let's say, and these are totally arbitrary, by the way. So I'm going to send up an array that goes off in this direction right here. Okay, now the reflection would be off at the exact same angle, meaning exactly like this. Notice the boxes. The boxes of the graph paper should help you. 6 over, 2 up. Well, 2 up, 6 over, right? Keep it the same. But what do I need? I need a back ray. Remember, every reflected ray has a back ray, right? So I have a back ray that's going to be going 2 up, 6 over. And I'm just going to keep going. I'm just going to trace it as long as it goes. Like that. Okay, so there's my first ray, my first incident ray, reflecting ray, and back ray. Okay, and now maybe I'll talk about another ray of light that comes off the top of the candle flame. And let's go down instead of up. Let's go down. So how about at an angle like this? Now notice what my angle is, okay? Notice my angle here. I'm going to go 6 over and 5 down. So my ratio is 6 by 5. So I need to have the exact same ratio. I need to go 5, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6. That would place it exactly like this. Right? Exactly like that. Okay, but I'm going to use blue to represent that. So now, even though the rays of light don't go into the box, I'm still drawing the extension of the reflection there to show where it'll end up. Okay, and I'm using the same ratio, 6 by 5, going up the other way. So 5 up, 6 over would put it over here. And then 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 would put it like that. So if I trace the back ray back through those dots, just like that. Okay, so far I've got that. Now, the next thing I'm going to do is I'm going to run some points. I'm going to run a few points off of the bottom. Let's run 2. I'm running 2, because again, every point has multiple rays going off in all directions. So I'm going to go 2 points off the top, 2 points off the bottom. Okay, because remember, we wanted 4 rays that emerge from this, okay? So I'm going to go 2 off the top, 2 off the bottom. So off the bottom, let me go something like this. How about, let's go, I'm going from that point there. I'll go up to this point right here. So notice my ratio is 4 over and then 3 up, okay? So I'm going to go this way, and it's going to reflect 4 over and 3 up. So it's going to reflect just like this, okay? Which means it's going to reflect that way, and it's going to have a back ray that goes exactly like this. Remember, the back ray is a virtual extension that you see inside the mirror coming back from the reflected ray. Then what I'm going to do is I'm going to go a little bit higher. So I'm going to go, let's see, maybe 4 over and, let's see, 1, 4, 5, 6, 7, 8. Yeah, how about this? Let's go 4 over and 1, 2, 3, 4, 5, 6, 7, 8, maybe 8 up. So something like that. So I think what I'll do, 1, 2, 3, 4, 5, 6, 7, 8. So what I'll do is I'll run a ray that goes 4 over 8 up, and it will reflect at that exact same angle, 4 over 8 up. So 1, 2, 3, 4, 5, 6, 7, 8. It will reflect back at that same angle just like that. Which means it'll be having a back ray extension that looks just like that. Now, do you see where the two are meeting right there? That is the height of the candle, right? And then there's the little thing, and then there's the edge of the box, right? So what do you get? You get an image that is exactly the same size as the object and exactly the same distance inside the mirror as the object. Section 22.2, Qualitative Analysis of Curved Mirrors. Draw light rays striking a concave mirror and light rays striking a convex mirror. Remember, every reflected ray has a back ray. All right, let's take a look at this right here. Well, when a mirror caves in around an object, that is a concave mirror. When the mirror bends away from the object, that is a convex mirror. Let's start with a concave mirror. First thing I'm going to do is I'm going to draw parallel rays of light. So I'm going to have one parallel ray coming in like this. Okay, and by the way, this thing right here, that has a name to it. That is called the principal axis. Principal axis. And I'll just be referring it to PA just as an abbreviation, okay? C is the center of curvature. And F is the focal point. We're going to see what that is too in a minute. Now, the center of curvature, if you literally kept this thing curving all the way around in a circle, you can see the center of curvature is right at the center of all that. Okay, that's why it has the name center of curvature. Okay, so that first parallel ray comes in, and it's going to reflect just like this. It's going to reflect right down through that point there called the focal point. And let's go ahead and draw a back ray extension up like that. Well, if we had another parallel ray come in like this, that parallel ray, guess what? It's going to reflect right through the focal point. There's the back ray extension right there. The same would be true for any parallel rays that happen below the principal axis. You have this third parallel ray coming in. Okay, what will it do? It's going to reflect this time upward through the focal point. There's the back ray extension. And then finally, if I draw a fourth parallel ray, it would reflect upward through that focal point. So what is a focal point? The focal point is the point at which all parallel rays will reflect through. Hence the concept of focus, right? If this were a direct TV dish, you'd have a little receiver there that all the radio waves are bouncing off the dish through that point to then receive that information. Now, for a convex mirror, it's a little different. If I have a parallel ray of light coming in, okay, now the way this one worked, the reason why it bounces this way is because if this represents a tangent line, there's your normal, you can see theta 1 equals theta r, right? In every instance. If I looked at this one here, here's my tangent line, here's my normal to the tangent, theta 1 equals theta r. Okay, it's law of reflection. Well, law of reflection would apply in this instance too. It'll come off at that angle such that the back ray extends back through the focal point. Okay. Again, if you looked at if we drew a tangent line here at that point, and then here's the normal, theta 1 equals theta r, law of reflection is intact. The easiest way to do this, though, is just find where the focal point is and make sure that your reflecting ray lines up with your back ray through the focal point. So if I do another one, parallel ray comes in like this. My reflecting ray is going to go off at an angle about like that, so that the back ray goes and extends through my focal point. If I have a parallel ray coming in at this angle, coming in like this, it will reflect off at an angle like this, such that a back ray would pass right through. And just do one more. If I have a parallel ray coming in like this, it would reflect off of that mirror at a really steep angle, such that the back ray comes in through the focal point like this. So notice for a concave mirror, reflecting rays go through the focal point. Let's make a note of that. Reflecting rays go through the focal point. For this concave or convex mirror, its back rays go through the focal point. So in both cases, something is passing through the focal point. Okay, but for a convex mirror, it's the virtual rays that are happening, that not the reflected rays. Explain what the center of curvature C of a mirror represents. Well, the center of curvature is basically the radius of curvature from what the mirror is cut. So again, if we take the whole thing and we make a circle or a complete sphere around it, it represents the center of that curvature, or the radius of the mirror. Explain what the focal point of the mirror represents. Well, the focal point is the point at which all parallel rays would reflect through, or in the case of a convex mirror, the back rays. Explain what the radius of curvature R in the mirror and what the focal length F of the mirror is. So the radius of curvature is the distance. Radius of curvature is the distance from the mirror to the center of curvature. Okay, it's denoted by R. The focal point is the distance of the mirror, focal length F is the distance from the mirror to the focal point. The focal point is always half the radius of curvature. If you look at the picture, this distance is always half of that distance. This distance here is half of that distance there. What is the difference between a real image and a virtual image? Real images form in front of the mirror. Virtual images form behind the mirror. Real images form from the intersection of reflecting rays. Virtual images form from the intersection of back rays. So let's make sure we understand the difference. Okay, virtual image behind the mirror, intersection of back rays. Real images form in front of the mirror. They form from the intersection of reflecting rays. What is the difference between an upright image and an inverted one? Well, upright images are oriented about the principal axis upright, meaning straight up. Inverted images are essentially upside down images and are oriented below the principal axis. For a single mirror, how are those adjectives always paired? Well, real images will always be inverted. Virtual images are always upright. What are the three rays we can draw to find an image produced by a curved mirror? So we're going to begin to learn how to draw what are called ray diagrams. Okay, all you need are two rays to intersect in order to form an image. I'm going to give you three rays. However, only two of these rays actually need to be used in practice. Okay, here we go. Ray 1 goes parallel to the principal axis and reflects through the focal point. So on diagram A, let's do ray 1, 2, and 3 together. So ray 1 goes parallel to the principal axis, like this. And it's best to just kind of draw it from the top of the object. This arrow, this upright arrow, represents whatever object is placed in front of the mirror. It could be a person, a candle flame. It could be you standing in front. It could be your face. It could be a pencil. It doesn't matter. It's some object placed in front of the mirror. And it's going to go all the way to the mirror. Okay. And so the principal axis would be this thing right here. Okay. And ray 1 goes parallel to the principal axis and then reflects through the focal point. So I'm going to reflect it, this angle here, right through that focal point. Just like that. Now I need to draw the back ray extension, like that. Reflected rays always have to have back rays. Okay, now ray 2 is the exact opposite. It's the converse. It's going to pass through the focal point and then reflect parallel. So we're going to go through the focal point like this. It's going to meet the mirror, just like right there. And then it's going to reflect parallel to the principal axis, just like that. There's your back ray. Notice your reflecting rays have converged at that point right there. Your back rays have diverged. That's going to be a major point of being able to identify this. Okay, now technically we could actually stop here because two rays have already intersected and those two rays happen to be reflecting rays, so it's going to form a real image. However, let's just learn what ray 3 is just so we can, well, learn how to apply it. Ray 3 will go through the center of curvature and reflect off the mirror back on itself. So for this one, you'd have to draw the curvature a little bit more like this, off to the side here, and it would pass through the center of curvature all the way down. It would reflect off that curvature of the mirror, and it would come all the way back up, just like this. Notice how it's meeting at the exact same spot. So this reflecting ray, that reflecting ray, and even that reflecting ray are all meeting at that same spot. That represents the tip of the image. And I would draw the image as an in this case, an inverted arrow. Since that intersection forms below the principal axis, we have an image the image is going to be real. Why? Because the image forms in front of the mirror. 2, it's going to be inverted because the arrow is upside down instead of right side up. And then finally, the arrow is shorter. See how it's 2 units long instead of 3 units like the object? This is 2 units long. The object is 3 units long. So it's going to be a smaller, the image is going to be smaller than the object is. Now in diagram B, we can see that the object is moved inside the focal length. Okay, so now let's take a look at our rules for ray diagrams and apply them. Remember, first ray goes parallel to the principal axis and reflects through the focal point. So we're going to go parallel to the principal axis, just like this. And we're going to reflect back through that focal point, just like that. And we're going to get that, so let me do the reflection ray in blue. Reflect through the focal point. And we're going to get that virtual back ray. Remember, every reflecting ray needs a virtual back ray. Then the second ray, if you remember, the second ray goes through the focal point and reflects parallel to the principal axis. So it's exactly the converse, right? Now, the only way you're going to do that is if you actually line up the focal point and the object with the mirror. So the first ray would go through the focal point, like this. You line up the focal point with the object and the mirror. Then once you reach the mirror, you reflect parallel. And you would have a parallel back ray going into the mirror. Now notice, if your reflecting rays are diverging, your back rays are converging. And the converging of those two back rays is where the image is going to be formed. Okay. Now, the third ray, remember how the third ray goes. The third ray, ray 3, goes through the center of curvature and reflects back on itself. So let's see how that one would look. You line up the center of curvature, C, with the top of the object, just like that. It reaches the mirror. Then it's going to reflect back on itself, just like this. And as it does, you can see the back ray is going to extend right back through the same spot where those are intersecting. So I could, as long as I have 2 of those 3 intersecting back rays, I'll know where the image is supposed to be formed. Since the intersection occurs above the principal axis, that means the image is going to be forming over here. So the image characteristics are the image is upright, virtual because it's behind the mirror, and larger. You can see how this arrow is longer than the object. Diagram C. What about when we take that object that is in front of a convex mirror? Well, the same rules apply. Okay, first ray goes parallel to the principal axis. When it reaches the mirror, it's going to reflect in such a way upward so that it's going to reflect in such a way like this, such that the back ray goes back through the focal point like that. Okay, now the second ray lines up with the focal point. It tries to go through the focal point, but it doesn't reach the focal point because it doesn't pass through the mirror. And it gets, so you line up the focal point right here, and you stop when you reach the mirror, and you reflect parallel. Just like that. And you draw your back ray extension. And if you were to use the third ray, which you don't have to, but if you were to use the third ray, you would line up the object with the center of curvature way over here, and you can see it extends all the way back to that point right about there. It reflects back on itself, and the back ray extension would go right through that spot. Okay, now since the intersection is forming above the principal axis, there would be the object right there, or the image, excuse me. And so the image that forms in this would be the image is upright, virtual, and smaller. You can see how this arrow is shorter than the original object. Section 22.3, the mirror equation. State the mirror equation and explain each symbol. Okay, well, the mirror equation is 1 over F equals 1 over SO plus 1 over SI, where F is the focal length, SO is going to be the object distance, the object distance is the distance from the object to the mirror, and SI is going to be the image distance. That's the distance from the image to the mirror. State magnification equations, explain the symbols. Well, first of all, magnification as a concept is the ratio of image characteristics to object characteristics. Okay, it's a ratio of image to object characteristics. So what we can say is M is equal to HI over HO. Or we could say it's equal to a negative SI over SO. Okay, now, what do all these things stand for? Well, M, that's the magnification. Magnification is just a way of saying how many times bigger or smaller is the image than the object. A magnification of 1 is what you see when you look in the bathroom mirror. Magnification of 1 means the image is the same size as the object. A magnification of 0.5 means the image is half the size of the object, or appears half as large. A magnification of 2 means the image appears twice as large as the object is. So magnification is again, it's that ratio of how the image looks compared to the object. Image to object characteristics. So M is magnification. HI is image height. Okay, it's the actual height of the image. HO is object height. Okay, you already know what SI and SO. SI is image distance. And SO is object distance. Image distance, object distance. Now, why the negative in here? Well, here's why. If we have an image distance that ends up being positive, okay, if SI is positive, that means it is a real image, and real images form in front of the mirror, which means you'd have a positive SI times that negative is negative divided by a positive value. You're going to get a negative magnification, meaning you're going to get an inverted image. So a negative magnification means inverted image. If SI is negative, then you're going to end up with a virtual image. So if SI is negative, we would have negative times the negative, which would be a positive, which would be an upright image. All virtual images are upright images. So the magnification negative there just kind of helps to kind of reaffirm that connection between the upright nature of a virtual image and the inverted nature of a real one. Find the image distance, image heights, and magnifications in the previous three diagrams. Okay, so let's write down some information. Before we do, let's take a look at how we would solve for these values. Okay, now, if the mirror equation is 1 over the focal length equals 1 over SO, the object distance, plus 1 over SI, the image distance, what we would do to solve for SI, we would first solve for 1 over SI, okay? Now you do that by subtracting 1 over SO. So 1 over SI would be 1 over F minus 1 over SO. So what we would do is we would take the inverse of this minus the inverse of this, and then we would inverse that difference to get SI. Okay, so that's how we solve this equation. Now, what we need, of course, is we need the focal length and SO in each of these problems in order to find the image distance, SI. Now, to find image height, you can use your magnification equation. If magnification is equal to negative SI over SO, you can solve for, well, actually, let me kind of bring that out. If magnification is negative SI over SO, but it's also height, image height over object height, you have a proportion that you can use. And so if we do our cross multiplying here, we get that negative SI times HO equals HI times SO. And when we solve for HI, the height, it's always going to be negative SI HO over SO. So that's the equation we're going to have for image height, okay, using that proportion. So let's give this a try. First of all, let's go back to diagram A and get focal length and object. We need focal length here, and we need object distance here. Okay, now if we look back at diagram A, you can see the focal length is 10 units away. I'm going to call each unit a centimeter, so 10 centimeters away. Okay. Or, you know what, let's just leave it as units. It doesn't matter because it could be centimeters, meters, whatever. Let's call it, it's 10 units away. Now, the actual object distance is 5, 10, so 5, 10, 15, 20, 25. That distance right there is our SO. That's what the object distance is. Now, the image distance you can kind of see from right here. You can see it's roughly about 16. Okay, it's a little over 16, okay, units away in front of the mirror. But we can confirm that with a calculation. SI, on the other hand, is, or SO rather, excuse me, is 25 units. You can see it's 25 units away from the mirror. So let's take all that information and let's write it down for a calculation. So for diagram A, we know that the focal length is 5 units, and we know that SO is 25 units. Okay, so the equation we're working with is, so we start with 1 over F equals 1 over SO plus 1 over SI. To solve for SI, we have to plug in for 1 over SI. So 1 over SI would be 1 over the focal length minus 1 over SO. So that's the equation we're going to be using to figure out SI. So 1 over the image distance is equal to 1 over 5 minus 1 over 25. So what we're going to do is we're going to go, wait, I keep saying 5. It's not 5, I'm sorry. 10 units. The focal length was 10 units on diagram A. My mistake. Please correct that. So what I'm going to do is I'm going to go 10 inverse minus 25 inverse. Let's take a look at this. Let's see, inverse minus 25 inverse, and then we have to inverse our answer. And you can see we get a little over 16, about 16.7. So SI is approximately about 16.7 units in front of the mirror. Since the answer is positive, right, we know that that positive means it's in front of the mirror. Okay, so there's the first part. Now, let's use the other equation for height to get the height of this thing. So height, HI, is negative SO, or we have the equation here, negative SI HO over SO. So image height is going to be negative, well, SI was 16.7 units times HO over SO. So now what we need to do is we need to kind of look at those values. So the object height, go back to the original diagram A. Object height appears to be 3 units high. Okay, it's so 1 unit, 2 unit, 3 units high, however that much is. And you can see that the image is 2 units high, meaning the image is 2/3 of the object. So if we kind of put the values in there, there we go. If the object height is, let's say, 3 units high, right, and the object distance is 25 units away, So then what I would do is my height is negative. What does the negative tell me? It's inverted. Negative height's inverted. So I'm going to go negative 16.7 times 3. So times 3 divided by 25, which was my SO. And you can see I get 2. Negative 2 units. So negative 2 units just simply means that it's going to be 2 units in an inverted direction. Okay, now what would the magnification be? The magnification, and I can just simply go HI over HO, and it's going to be 2 units, or negative 2 units, divided by HO, which was 3 units. And so I get a magnification of negative 2/3. Now, what does a magnification of negative 2/3 mean? Or I should say negative 0.67. What does this magnification actually mean? It means the image is 2/3 as large as the object. Okay, again, the negative means it's inverted, but the actual number, it tells you how big the image is compared to the object. Okay, let's take a look at diagram B. So for diagram B, okay, the focal point is still, F is still 10 units, but this time SO is 5 units. It's really close. It's closer to the mirror, actually. And you can see that SI over here is going to be somewhere like greater than negative 6. Okay, so it should be over on that far side of the mirror. Okay, it's going to be negative something on the other side of the mirror. We should expect the height to be larger. So if the HO, the object height is 2 units, we expect the image height to be 3 or greater units because it's going to be bigger. Okay. So for diagram B, the focal length is still 10 units, but this time SO is 5 units. So we're going to go 1 over SI is equal to 1 over F minus 1 over SO. So 1 over SI is equal to 1 over 10 minus 1 over 5. Or you're going to go 10 inverse minus 5 inverse. Okay, so SI, the image distance, clear this, we're going to go 10 inverse minus 5 inverse equals, and then we're going to inverse that, and we get negative 10. Negative 10 units means the negative means it's behind the mirror. That tells you how far away it is behind the mirror. Okay, so the image height is going to be negative SIHO over SO. So if we plug into that, negative times negative 10 units times, remember the object height was 2 units high, over the object distance, which was 5 units. So if you look at what we have here, that goes into that 2 times. Negative, negative cancels. And 2 times 2 means we have an image height of about 4 units. That makes sense because we had a bigger unit. Now, it's positive, which means it's going to be upright. Positive height is upright. Negative height is inverted. Finally, our magnification will just simply go high over ho, hi over ho, and the image height was 4 units high. The object height was 2 units high. The magnification is 2. What that means is the image is twice as large as the object. Okay, and then finally, diagram C. Diagram C has a focal length inside the mirror. So the focal length this time is going to be -10 because it's behind the mirror, not in front of the mirror. The object is placed 10 units. I keep wanting to say centimeters. It's just generic units. Could be meters, centimeters, whatever. The object is placed 10 units in front of the mirror. The image seemed to form between 5 and 10 centimeters behind the mirror. Let's take a look at the analysis of this one. Okay, so the focal length for this one would be -10 units. SO, the object distance, would be 10 units in front of the mirror. Okay, 1 over SI is 1 over the focal length minus 1 over SO. So 1 over SI is equal to -1 over 10. Or you could actually do it this way. We could do 1 over the -10 focal length minus 1 over 10. In other words, it's going to be -10 inverse minus 10 inverse is how we're going to calculate that. Okay, let's try it. Let's figure it out. SI, let's see. We're going to go, so 10 negative inverse minus 10 inverse equals, and then we have to inverse that final answer, and we get a value of -5, which seems to kind of fit because it was supposed to be around 5 units behind the mirror. So that means negative again means behind the mirror. Okay, that many units behind the mirror. All right, the object or the image height, again, -psi times HO over SO. So let's go ahead and take a look at some of those values again. We need the object height in C appears to be about 4 units high. This appears to be about 2 units high. Okay, let's verify that. So we have the image height, so we have negative times -5 times the object height was 4 units high over the object distance, which was 10 units. So what do we have here? Negative times negative is positive, and 20 over 10 means the image height see. So you can see if this is 5 units, and that's 4 units divided by 10 units, right? That's going to be essentially 20 divided by 10, or the image height is going to be 2 units high. Okay, now it's positive 2 units, which means it's going to be upright. But it's going to be a positive 2 units for the image height. Okay, and then finally, the magnification, if we just simply go high over ho, or you can go negative psi over so, it's fine too. But it's going to be what, 2 units over 4 units high, or 0.5 or a half. So what that means is that the image is half the size of the object. Okay. So we are going to actually fill out this chart in class after we have completed all of our ray diagrams. So once we have completed all of our possible ray diagrams, we've only done a few in this video tutorial, but we're going to do much more in class. And after we've completed the whole thing, we'll use this as a summary of all of our work with ray diagrams. So we're going to hold off onto this and skip this section for right now. Section 22.4, Qualitative Analysis of Lenses. Explain the difference between a converging lens and a diverging lens. Show parallel rays passing through each. Okay, well, this is referred to as a converging lens. I'm going to write that over the top. This is converging lens. This is known as a diverging lens. Okay, now these names are given based upon the way the rays react with the refraction of light through these lenses. Now, another name for this would be convex, right? It's kind of like a convex mirror, right? But it's convex on both sides. Therefore, this is called a biconvex lens. You'll see it named that as well. Same thing with a diverging lens. It looks like a concave mirror, but it's concave on both sides. Therefore, this would also be called a biconcave mirror. Okay, so what do you notice here? Converging lenses are going to have parallel rays of light all refract through the far side focal point, just like you see here. Okay, now something to consider, just like we had in the previous section. Let's write this down. Just like all reflected rays have a back ray, all refracted rays will be drawn with a back ray extension. We did that with all of our reflected rays. Now we're going to do that with our refracted rays. So this right here, this right here, this right here, and this right here are all refracted rays. And I should draw each one of them with its own back ray. So you'll notice the back rays are diverging in front of the lens, while the refracted rays are converging through the far side focal point, hence the name converging lens. Okay, now what does a diverging lens do? A diverging lens is going to take those parallel rays, okay, and it's going to spread apart. It's going to diverge in such a way at an angle much like this, such that the back ray passes through this point right here. Okay, notice the pattern that's being developed here. Okay, that makes this a focal point. But it also makes this a focal point too. That means lenses actually have two focal points. Okay, and why is that? Because light can pass this way and refract through that far side focal point, and light can pass this way and refract through this far side focal point. So since light can pass through a lens two different ways, lenses have two different focal points. Now for a diverging lens, it's the back rays that pass through the focal point instead of the refracting rays. Does a lens have a focal point the way a curved mirror does? Does it have a center of curvature? A lens actually has two focal points because it has two surfaces of spherical curvature. It also has two centers of curvature extending beyond the length of each focal length. The diagrams below show parts of the thin lens that have been zoomed in very close. Shaded regions represent higher index of refraction than white regions. Trace the ray of light to indicated through the lens to the other side. What would this look like? Okay, so this is going to look very similar to the exercise we did with the Snell's law of refraction and the prism, the triangular prism. Okay, so what I'm going to do with this is I'm going to draw a kind of like a tangent line, so to speak. I'm going to draw a tangent line right there, about kind of like that. And then I'm going to draw a normal to that tangent line. Okay. That would make this theta 1 coming in. Okay. Now, if I extend the normal into the lens, just like that, it means I'm going to refract closer to that normal. So I'm going to start to bend like that. Where this angle here, right there, that's my theta 2. That's my smaller angle. Then I reach this other side, okay, which I'm going to have another tangent line. I'm going to have another normal, just like that. But this time we are going from the lens out back into air again, which means the light is going to refract farther from the normal. So I should expect it to be a much larger angle right here. And look which way it's pointing. You can see the ray of light is converging downwards, just like we saw right here. Okay, so what would happen if the situation were reversed? You have a converging, kind of a converging shape that is hollowed out on the inside. Well, what would happen? Let's get ourselves a surface, normal. We would bend farther from the normal. Just like that. Okay, then when we reach the other side, you've got your surface, you've got your normal, okay, and this represents our theta 1. We would bend much closer to that normal over here. Okay, notice it starts to bend upwards and kind of diverge a little bit. Okay, how about what's going to happen with a diverging lens like this? Well, again, here's my tangent line to the surface, which means here is my normal, there's my theta 1. Extend my normal into the page, and I will be bending closer to the normal, just like that. Okay, then here's my surface, just like that. There's my normal to the surface, and I'm going to be refracting farther from the normal because I'm going back into air again. So I would expect me to refract farther from that normal, creating a very large angle out here. And notice I'm diverging upwards like we see here. Okay, now the opposite is true for this one. Here's my normal. Okay, and I'm going from high optical density to low optical density, so I should be refracting farther from that normal, like that. So there's my theta 1, there's my theta 2, it's going to be a lot larger. Okay, then I get to this surface. And I'm going to now be refracting closer to that normal. There's my theta 1, and I'll be refracting closer to it on the other side. Looks something like that. Briefly state what makes a converging lens and what makes a diverging lens. Well, converging lenses take parallel rays of light and converge them through a far side focal point. Diverging lenses take parallel rays of light and spread them out such that virtual rays, back rays, extend backward through a near side focal point. What are the principal rays that we draw for a lens? Well, they're very similar to the rules for ray diagrams for mirrors. Ray 1 will go parallel to the principal axis. This time it's going to refract through a focal point. Ray 2 is going to go through the other focal point and refract parallel to the principal axis. Ray 3 is the easiest one of all. It is literally just going to go through the center of the lens, unrefracted. Okay, let's put these into practice. Diagram A. So I'm going to have a ray of light go to the top of the lens like this, and it's going to refract through the far side focal point just like this. So parallel to the principal axis, refracts the focal point. The second ray is going to go through the other unused focal point, just like this. It's going to get to the lens right about there, and it's going to refract parallel to the principal axis. Now, I do need to draw my back ray extensions, right? Every time I have a refracting ray, I should have back ray extensions. The third ray is super easy. It literally just goes through the center of the lens. As soon as I get here, I'll change the color. Essentially unrefracted. Notice where all those three refracting rays are meeting. That the point of intersection is below the principal axis. So what we notice for this one is the image is, now this time the image is going to be a real image. Why? Real images form on the far side of lenses. Think about that. Mirrors reflect the light in front, so real images would occur in front of a mirror. What do lenses do? Lenses refract light on the other side of the lens. So real images form on the far side of lenses as opposed to the near side of mirrors. And how else do we know it's a real image? It's inverted. All real images are inverted. So it's real, it's inverted, meaning it's upside down, and notice this is 2 units high compared to 4 units high. It's about half the size, right? So it's smaller. The image is smaller than the original object. Okay, now let's move the object inside the focal length and repeat those rules. So we're going to go parallel to the principal axis. And then we're going to go through the far side focal point, just like that. There we go. Draw your back ray extension. Okay, then you're going to line up the focal point with the other, line up the object with the other focal point, and you will refract parallel. There's the back ray extension. Okay. Now notice, and then the third one is to just go through the center of the lens. So if I go through the center of the lens, it would be like this. Kind of unrefracted, but then if I follow the back ray back through this, you can see it's kind of meeting at a very similar spot. So I'm not going to focus so much on that third ray. Let's just focus on the 2 we have so far already. I think I can probably make this a little neater. Yeah, so it's going to end up kind of over here. There we go. And okay, something like that. There we are. And then the center of the lens. If I back that up right through there, you can see they all go through the exact same spot right there. And so my image is actually formed right here. Notice the image is drawn from a point of intersection above the principal axis. So the image is, well, number 1, it's a virtual image. Okay, how do we know it's a virtual image? The image forms in front of a lens instead of behind it. Number 2, it's upright. You can see the orientation of the image is the same as the object. It's upright. And you see the image is larger than the object. It's magnified, larger. Okay, now in diagram C, you're putting your object in front of a diverging lens. Okay, so the rules still apply. The first ray goes parallel to the principal axis, and then it's going to go through. It's going to diverge in such a way like this that the back ray goes back through the near side focal point, just like that. Now, the second ray tries so hard to go all the way over to the other focal point, but what happens is when it gets to the lens, it's going to stop. Well, not stop, but it's going to stop going in that direction, and it's going to run parallel or refract parallel to the principal axis. And then, of course, I've got my back ray. And the image would form from those two intersecting back rays. All right, we have our intersecting back rays forming a virtual image. So when back rays intersect, we form a virtual image. When refracting rays intersect, we form a real image. So the image for this example is virtual. It's upright. And notice the image is smaller than the object. Section 22.5, thin lens equation and qualitative analysis of lenses. Well, the thin lens equation is exactly the same as the mirror equation. That's why this is called the mirror lens equation. So all the variables are the same, the equation's the same. And the concept of magnification is exactly the same. So nothing changes. All right, so remember, to find the image distance, think about what we did last time. We went 1 over SI was 1 over the focal length minus 1 over SO. And to find the height, think about what we did to find the image height. The image height was negative image distance times object height over image height. Okay, remember we used that. All right, so let's take a look. Diagram A, let's go back and look at diagram A. Diagram A, the object was placed 5, 10, 15 units away. Okay, you can see the focal length is 5 units away, and the object seems to be about 4 units high. The image, as you can see, appears to be about 2 units high, and it appears to be, I don't know, between 5 and 10 units beyond the far side of the lens. Okay, so taking that information, we need focal length and object distance. So focal length is 5, object distance is 15. So focal length is 5 units. Object distance is 15 units. So we are going to go 1 over SI would be 1 over 5 minus 1 over 15. That's going to be 5 inverse minus 15 inverse, and then inverse your answer. So 5 inverse minus 15 inverse, subtract, and then inverse your answer, and we're getting about 7.5 units high. So SI is not high, but far. 7.5 units. Since the answer is positive, it means on the far side of the lens, behind the lens. Okay, let's find how high the image was. So the image height was negative psi times ho over so. So negative 7.5 units times the image height, which was 4 units high, if you remember, divided by the object distance, which I think was 15 units. So, well, 7, this actually works out pretty well because 7.5 actually goes into 15 2 times, and then 2 times 4 means that the image height would be negative 2 units high. The negative means it's going to be inverted. Okay, and then finally the magnification, we could use image height to object height, and it would be negative 2 units over the object height, which was 4 units, or negative 0.5. So again, what does the negative mean? Inverted. What does 0.5 mean? Well, it means the image is half the size of the object. Okay, now diagram B. Let's figure out, we need the focal length and we need SO in order to complete the calculation. So the focal length for object B, the focal length is 10 units. Object is placed at 5 units. So focal length is 10 units. Object is placed 5 units. Okay, so 1 over SI equals 1 over the focal length, 10, minus 1 over SO, which is 5. Okay, we're going to go 10 inverse minus 5 inverse, then inverse our sum. Ten inverse minus 5 inverse equals, and then inverse our sum, negative 10 units. What does that negative mean? It means in front of the lens. Specifically 10 units in front of the lens. Okay, if we go back to diagram B, that's exactly what we saw. The image forms about 10 units in front of the focal. In fact, it forms at about the focal length. Okay, now HI is equal to negative psi ho over so, which would be negative times negative 10 units times the object height. How big was the object? The object appears to be about 1 unit high. Negative, negative cancels. The object height was, or the object distance was 5 units. So we get an image height of 2 units high. Positive 2 units high. Again, positive means it is upright. Magnification, HI over HO, so it's going to be 2 units high divided by the object height, which was 1 unit high, which means we get a magnification of 2. So what it means is the image is twice as large as the object. And we can see that from the picture. The image is 2 units high, the object is 1 unit high. The image is appearing twice as large as the object. Okay, now diagram C, we need the focal length and we need the object distance. Okay, well, the focal length is still 10 units. The object distance, and the focal length is actually going to be negative 10 because it's back rays that pass through the focal length, not forward rays, not refracting rays. So for a diverging lens, just like a convex mirror, the focal length is going to be negative. The object is placed 15 units in front, and it appears to be object is about 2 units high. So let's use that information. Focal length is going to be negative 10 units. The object is placed 15 units in front. So 1 over SI would be 1 over negative 10 minus 15. So we're going to go negative 10 inverse minus 15 inverse, and then inverse our answer. Okay, we're going to go negative 10 inverse minus, we were going 15 inverse, equals, and then we need to inverse that answer, and we get about negative 6. Again, negative means it's going to form in front of the lens, 6 units specifically in front of the lens. Okay, there we go. And let's just double check with the diagram. So here, yep, that fits. 6 units away from the lens, or specifically in front of the lens. Okay, finishing off our calculations for image height, we're going to go negative 6 units times the object height, which I forgot how high it was. It was 2 units high. Okay, divide that by negatives to cancel. The object distance, which was 15 units. Okay, so you can see we're going 12, 6 times 2 is 12 divided by 15. 12 by 15 is about 0.8. So it's roughly about 0.8 units high. Okay, let's check with the picture. And that kind of makes sense because what do we have here? This is 2 units high. The image height is a little less than 1 unit high, so being 0.8 units high does make sense. It's positive, which means the image is upright. And then finally, magnification is image height to object height, which would be 0.8 units to 2 units, which would be a magnification of 0.4. What that means, since it's positive, it means it's upright. The image is 0.4 times as large, or you could say 2/5 as large as the object. Okay. Again, we're going to be finishing this summary in class after we complete all of our ray diagrams. It will make more sense as to when a lens creates a real image, a virtual image, same size, larger size, but I want to make sure we go through all of those scenarios together. Section 22.9, telescopes and microscopes. Well, telescopes and microscopes have what is called a compound system, meaning more than one lens involved. Okay. Now, for a microscope, it's a lens on the eyepiece and a lens on the rotating objective that you put right above the object that's on the slide, okay, on the glass slide. Well, a telescope has an eyepiece and it has a lens on the other side, and it has a mirror to kind of reflect that light to the eyepiece. So here's what we have. We have two identical lenses as shown with focal lengths of 10 centimeters apart and are placed 10 centimeters apart as shown. An object is placed 20 centimeters in front of the first lens. Trace the rays from the object to the final image. Okay, so here's what we would end up with. The way this works is, let's write this down. The image of the first lens becomes the new object for the second lens. Let's see how that works. The first ray goes parallel to the principal axis. It gets to the lens, and it's going to refract through the focal point. Now, remember, the focal point for the first lens is 10 centimeters away, which happens to be the center of the second lens. So it's literally going to go through the center of that second lens unrefracted, just like that. There's our first ray. Draw your back ray. Okay, now the second ray goes through the first unused focal point. It gets to the lens, and it is going to refract parallel. Just like that. Now the problem is it's going to meet that second lens over there, and what it's going to do right there, remember what parallel rays do? Parallel rays are going to refract through the far side focal point, and that's exactly what it does. It's going to refract through, so you have back rays extended back from this first lens, but it's also going to refract through this point over here, right? You've got that back ray extension right there too. And you can see where the image is going to be formed. The image is going to be formed where those two refracting rays will meet. Okay, this is a special case when two identical lenses are placed at each other's focal points. In general, when dealing with two lenses, we essentially let the first lens, the image of the first lens, become the object of the second.